Very good morning. Welcome you all to the NPTEL course on Advanced Distribution System Analysis and Operation. Today we'll focus on how to model distributed generations. With the inclusion of distributed generators in the distribution network, there will be two components of branch current matrix, one because of loads and the other because of distributed generations. Thus, net branch current matrix need to be computed before computing the net branch current matrix embedding the effect of loads and distributed generators. The net contribution, that is current injection at each bus integrated with distributed generators, need to be computed first. Now, the DGs are of different type. Assuming it is a PV type, bus voltage magnitude V and real power injection P both are actually known, whereas the reactive power Q, injection by the DGs and the PV bus voltage phase angle delta, they are not known to me. Now, in the process of modeling of distributed generations, the step 1 would be scan your bus data to find all PV type distributed generators, that is those with fixed voltage magnitude and specified real power output. Means in a given distribution system, identify the PV type buses of the whole system. Now, step number 2, record each PV bus specified voltage magnitude and real power injections. Step number 3, construct an impedance matrix Z. This matrix captures how an injected current at one PV bus affect voltage at itself and at every other PV buses. That is, the Z bus that you are supposed to make is the diagonal element, which is total path impedance from the source to each PV bus, and the off diagonal elements shared path impedance between pairs of PV buses. Now, just imagine we have distribution network, which is like a black box. We have all the buses and we have connected different PV type of DGs, which could be 1 to n. Now, in case of step number 4, we will formulate the voltage mismatch equation, that is delta V, which is Z times delta I, both are matrices, where gamma 1, gamma 2 up to gamma psi are known as set of PV buses, 1, 2 up to psi indices of the set gamma, psi the total number of PV buses in the network, delta V gamma x is the difference between magnitude of computed and specified voltage at the PV bus, delta I gamma x is the complex current injection required at the PV bus x to compensate the net voltage deviations. Moving to step number 5, the delta Z, delta I, delta V represent the impedance matrix, current injection matrix and the voltage mismatch matrix respectively. Now, similar to delta Z, we can calculate delta I as well as delta V as mentioned in equation number 17.2 and 17.3. Moving to step number 6, similarly, matrix Z can also be written in terms of real and imaginary component, that Z equal to R plus Jx, and we can rewrite the matrix R as well as matrix X as per the equation 17.4 and 17.5. Step number 7, using equation number 17.3 to 17.5 in 17.1 and splitting 17.1 into real and imaginary part, the resulting equation in compact form will be given by delta V R and delta V Q is given by XR minus RX, delta IR and delta IQ. Moving to step number 8, for any PV bus, say gamma X, the voltage mismatch equation has only real term as delta V gamma I, which is the difference between V gamma X specified minus V gamma X. So, the imaginary part of voltage mismatch will have value 0. This will be applicable for all the PV buses existing in the network, that is V gamma 1, V gamma x to V gamma psi, all is considered to be equal to 0. That means delta VQ become my 0. Also, real power requirement for the PV bus are constant. So, delta IR for the PV bus is considered to be 0. So, previously we have seen delta VQ is 0 and delta IR is also equal to 0. So, in compact form 17.6 can be rewritten as x times delta IQ equal to delta VR. So, the previous equation now being simplified. In this equation, the moment you substitute delta VQ equal to 0, and then you can substitute delta IR equal to 0. So, you could see that it is simply this is 0, this is 0. So, delta VR is now given by x times delta IQ. Now, moving to step number 9, the above equation for calculating additional reactive current injection can be utilized for computing net reactive power injection by assuming all bus voltages being close to 1 per unit, and the phase angles become extremely small. Thus, following equations prevails for a PV bus gamma x as given by delta V gamma 1 to gamma psi x matrix multiplied by delta I gamma 1 to gamma psi, equation number 17.8. Now, moving to step number 9, the total reactive current injection at PV bus gamma x at the beginning of iteration t is given by the following equation: I gamma x iteration t equal to delta I gamma x iteration t plus xi 1 to t minus 1 iteration delta I gamma x of the jith iteration. That is my 17.9 equation, which is very, very important to converge. Now, once the additional reactive current injections are computed, the computed injection has to be reflected in branch current. For this, net branch current matrix J needs to be computed, which will embeds the effect of branch current due to load J as well as branch current due to additional PV injections. Now, this is how actually the J matrix can be calculated using the following algorithms, the detailed algorithm which has been explained. So, first of all, you compute all the elements, okay, 17.2, store all the PV bus location information in an array gamma of dimension psi and x indices of PV, initialize a null number delta f of dimension m is to n, and then for I equal to 1, you can repeat till, and then finally, once the do loop is over, then we can come to formulate net current beyond branch matrix F by adding F with delta F and compute net branch current matrix. Delta F is additional PV current beyond branch matrix, and for I equal to 1 m, you can repeat, calculate the value of J as discussed, summation of F I J plus delta F I J, and finally, you can close with J is the net branch current matrix. Now, let us overally try to summarize the flow chart of implementing graph-based load flow. So, let us get into slowly, read system data, assign voltage for all the buses, calculate the connectivity matrix E, weighted connectivity matrix W, and bus branch topology matrix T. Initialize the iteration, and then you can move to compute the net current beyond branch matrix J and branch current matrix J, and then you move to compute voltage drop matrix and slack to other bus drop matrix, compute the new voltage, determine the voltage deviation delta V, and if the delta V is belongs less than epsilon tolerance value, and if it is yes, then the solution converges, you come to an end. If it is not, then actually you reinitialize the V old equal to V new, and then move to T if the T is less than T maximum iterations, and if it is yes, then you actually come to initial stage. If it is no, then solution does not converge and you come to an end. So, this is how actually the graphical based load flow analysis is being solved, And you might have seen there is no matrix inversion and there is no serious computation involved, which is mostly prepared for our distribution systems. Now let us see how this, because there is a question all the time, because graphical method versus conventional method, how it is going to perform. But it has been found that the graphical method is also performing better, or at least equally performing compared to classical techniques. So first of all, the proposed load flow algorithm was tested on a IEEE 33 bus system, and you could see that this is my bus number 1 to 33, and the percentage error for each bus has been calculated, and the percentage error in bus voltage magnitude when compared with, you know, benchmark value obtained using BIBC approach for IEEE 33 bus system. And you could see the percentage error is very, very reasonable. I mean, though they are varying, but it's quite reasonable. Now, the same thing has been tested for IEEE 69 bus system, and here also we could see the percentage, variation is very, very minimal. Now, the proposed load flow algorithm was tested on a IEEE 33 and IEEE 69 bus system, and you could see the maximum voltage error found to be minus 0.022 percentage for IEEE 33 bus and minus 0.0036 percentage for IEEE 69 bus. So the maximum bus voltage magnitude error versus BIBC benchmark were very small in both the cases. And just to test the robustness and the convergence behavior, I mean, it tested robustness by varying R by X ratio and loading factor on the IEEE 33 bus network, compared convergence speed against BIBC, current injection, and Z-bus methods. Now, current injection method is going to be this way, and the Z-bus method is going to be calculated to be this one, and the BIBC approach is going to be this one, and the proposed graph method is going to be this one. So if you see the proposed method, which is not very far away from other classical methods. I think further the robustness and convergence behavior with different loading factor has been tested, and the proposed method is still performing as expected. So results in table 17.1 and 2 show the proposed algorithm converges significantly faster, maintains repeat convergence across the wide range of by-X ratios and loading conditions. So we try to see the program, the graph-based load flow algorithm is not only working for a given R by X ratio, but with varying R by X ratios, and with different loading condition, we found it is convergence is as good as other classical techniques. It maintains repeat convergence across a wide range of R by X ratio and load conditions as mentioned, demonstrate high robustness and efficiency of the developed load flow approach. So if you are going to change the loads with different load models, we'll try to carry out the similar kind of analysis. Now, process for load flow analysis with different load models, because previously we integrated with different distributed generators, and now we are talking about load models. So previously generator model, and now it is actually load modelings. So they developed a graph-based power flow approach for radial distribution systems, formulated connectivity E and bus branch topology T matrices to represent network structure, utilize supporting matrices, load current beyond branch F, branch current I, voltage drop D, and source to bus drop L. Load current beyond branch matrix F will accommodate various load models, constant power, current, and impedances. Formulated a sensitivity matrix for PV bus models to compute net reactive current injection for voltage compensation. Net injection are integrated into power flow via PV current beyond branch and net branch current matrices. Modification of matrix F is required to accommodate different load models as it's mentioned. So we need to modify depending upon different load conditions, but at least we'll start with actually a couple of different load models in our discussions. Now, majorly we'll focus on actually constant power, constant impedance, and constant current, but if you're going beyond, probably actually you have to readjust your F for different loading conditions. Now, load current beyond branch matrix F for different load models. This matrix stores the load current existing beyond each branch in the network, and suitable operation on it will provide current flowing through each branch. The load current computation procedure is not uniform throughout the network since there are varieties of loads such as constant power, constant impedance, and constant current. This matrix computation depends upon the branch topology matrix and load current computation. Now, load current beyond branch matrix F. The load current beyond branch matrix F can be expressed as we discussed earlier. The F is defined by T ij times Sij upon Bj times Bjx, which is Tij Ii, and where Vj is the complex voltage, Ij is the complex current, and Sj is the complex power of the load, and Ti is the element of bus branch topology matrix. The value of x is either 0 if the load is constant power, 1 if the load is constant current, and 2 if the load is constant impedance. So, this formula can be used for any type of loads. Like earlier case, actually we can also have a graph based load flow with different load models. It is almost same. You read the data, assign voltages at all the buses, determine E, W and T, then initialize the iteration. And this is important. Compute net current beyond branch matrix J and branch current matrix J for different load models. And once this is done, you compute the voltage drop matrix, and then you come for the determine with voltage deviation. If it is less than epsilon, then you actually solution convergence. If not, you actually reiterate with a new parameter and moves on whether it is solution exists. If not, then you can move to the same point and start computing net current beyond branch matrix J and branch current matrix J for different load models. Repeat the cycle till you completely converge. Again, we repeat this application to different case studies. We have chosen two different things, two different case studies, IEEE 33 bus and IEEE 69 bus network used to validate these algorithms. And load models, so we evaluated on constant power Cp, constant current Cc, and constant impedance Cz, and composite JIP loads. And from this you can see with different bus numbers, so different loads, okay. We have plotted the voltage magnitude variation, percentage voltage magnitude error. This is further for IEEE 33 and 69 buses. And what we found that PV/PQ type distributed generations test result of IEEE 33 bus system has been determined, and you could see the voltage profile for both the system before and after DG inclusion are provided, and voltage magnitude comparison for IEEE 33 bus systems, and with the base case as well as with the distributed generators. And then the same thing repeated for 69 bus system. And with this, what we like to conclude here, with different type of load models, with different type of DGs, we can still apply graphical method distribution load flow algorithms. And for both IEEE 33 bus system and 69 bus system, the performance of the proposed graphical method for distribution load flow seems to be close to classical techniques. Thank you.